Hey there, super nerds. Sorry I couldn't be with you today. We are on a math retreat with the math department making math jokes. But I'd rather be hanging out with you guys. So, we are checking out the beginning of experimental and theoretical probability, our new unit. You'll have new seats next time I see you, and so let's get rolling. Just as a warm up, what I'd like you to try in your notes after you put this title in there is add these fractions. Yeah, turn this into a fraction, turn that into a fraction, add them up, leave it as a percent. See what you can do with that. Pause me until then. Pause. Sweet. Okay, so here we go. This is 1, 2, 3, 4, 5 pieces. So it's a whole broken into 5 pieces, and 3 of them are shaded in, so 3/5. We're adding to that. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So this is broken into 8 pieces, and 3 of them are shaded in. So we have 3 out of 8 and 3 out of 5. And so we're going to have to add those up, but the problem is this is a different size piece than this. We can't really add them until they have common denominators. So an easy common denominator would be found by multiplying this whole thing by this denominator and this whole thing by that denominator, right? So let's multiply this by 5/5. We're multiplying by 1, so we're really not changing anything, and we're going to multiply this side by 8/8, which is 1. We're not really changing anything, except for how the fraction looks. All right, so in the denominator, when you multiply those, here you'll get 40 and 24, and here you'll get 40 in the denominator. When you multiply these two, right, these give you the 40, and in the numerator you get 15. Yeah, so this should give us, 39/40ths, which is really close to a whole, so it should be around 1. And if you figure out what to change this into, we want to change the denominator to make this as a percent. We want to change the denominator into 100, and so what we can do is figure out what we can multiply by. If you multiply top and bottom here by 2.5 and 2.5, this is one way to turn this into a percent, because the denominator will give you 100. Oh, I guess another, you could divide by 4. That might make this really ugly. This turns out to be, what, 9, 2, 3, so 9, 97.5. Right, let me verify that. Yeah, 97.5. So this ends up being 97.5%. Sweet. So there it is as a percent. Now, this is a little fussy. I probably wouldn't give you something that has this much of a decimal to multiply by, but you get the idea. Cool. Neat. Moving on. So what I'd like you to do today is to be able to talk about sample space of a probability experiment and be able to calculate simple theoretical and experimental probability. So let's get rolling. You probably already know some probability, and we'll work on those sort of things together. Let me pop these so you can pause them and put them in your notes if you need. But basically, an experiment is where an activity something is being observed. A trial is each time we make that observation, like a coin flip. An outcome is the result. We'll get into sample space. We'll talk a little bit more about that. But we also have impossible events that can't happen. Zero probability, a probability of 0. Certain events have to happen. Probability of 1. So, but these are the basic definitions that I'd like you to know. So jot these in your notes. Probability is the measure of how likely something is to occur. The outcome is the result. The sample space is the set of all outcomes. That one we'll talk about because that one gets a little fuzzy for people. An event is the outcome itself, right? Probabilities range in percentages from 0 to 100, or 0 to 1 as a decimal. Great. Okay, so sample space is really all of the outcomes, right, for an event. So, like flipping a coin, flipping one coin, it can either land heads or tails. Now, you can argue that it could land on the edge, but let's say we sharpen the edge down so it never does that, right? And wiggle the table so it never lands nicely. It either lands heads or tails. Come on, man. Come on. So here are our two situations. You could get a head or the tail. Yeah, right? And so the sample space is this happens or this happens. One of those two things happen, right? One or two. So the outcomes, the number of outcomes in the sample space, here is two. There are two outcomes. It's either heads or tails and nothing in between. Same thing for rolling a die, right? When you roll one die, dice is two, is plural. Die is singular. You roll one die, it could be, you could get a 1 or a 2 or a 3 or a 4 or a 5, right? So there are 6 outcomes in the sample space, right? This is the sample space because it's everything that could happen if you roll the die. Great. Same sort of thing with pulling a card from a deck. The outcomes are any of the cards in the deck, and there happen to be 52 cards in the deck unless your little brother has eaten some of them, right? So this has 52 outcomes. Neat. Great, moving on. So that's sample space. Everybody gets a sample. All right. So theoretical probability is what we think will happen just based on the numbers and theory. Right? So theoretical probability, you can write this piece down, is the number of outcomes that we want. We talk about favorable or desired outcomes. It's what we want divided by the number of outcomes that could happen, right? And this is the sample space, right? The number of outcomes in the sample space. So let's look at this one. If we want to spin a blue, right? If we want to spin a blue, well, let's see. There's one blue section, right? This is, let's do it in blue. This is what we want, and there's only one of them that we want out of the 1, 2, 3, 4 possibilities, right? So the probability to spin a blue is 1/4 or 0.25 or 25%, right? They're all the same thing. This guy, to spin a red, should have done that in a different color. To spin a red, well, there's two outcomes that would work for that. It's either this section or this section. So it's 2 out of 1, 2, 3, 4. So 2 out of 4 sections would work for us. So that's 0.5. It's 1/2, 0.5, or 50%. Right? That's the probability. Cool. So let's call that 50%, just so you see that they can be in fraction, decimal, or percent form. Same thing here. To roll a 2, to roll a 2 on here, oh, spinning wheel of death. There's only 1 2 on a die. So this is 1 out of the 6 possibilities that we saw in the sample space. And rolling an even number, well, evens are 2, 4, or 6. So there's 3 possibilities out of those 6 possibilities total sample space, and that's 1/2 or 50% or 0.5. Cool? Great. Let's move on. All right. So this is expected outcomes, and when we're looking at some expected outcomes, we're really solving a proportion. Let me give you an example. How many times would you expect a spinner to land on red if you spun 4 times? Well, okay, let's spin it. So there, oh, I got one. I got another one. I got another one. And, oh, I got all of them red, right? That's fantastic, but it's probably against the laws of probability, right? That's less probable to happen. Really, we would say there are 2 out of 4, right? This is the probability of landing on red normally. And since I have 4 spins, I would expect 2 of those 4, right? So really, this is we would expect 2, right? Since 2 out of the 4 times you spin, because we would expect that you spin once and it might land on this one. You spin another time, it might land on that. You spin another time, it might land on that. They each have an equal probability, and 2 out of those 4. So if you spun 4 times, you should get 2. 2 that land on red. Let's do that with a little bit something tougher. How many times would it land on blue if we spun 8 times? Well, it's only got one blue chunk here, so you'd expect blue 1 out of 4 spins, right? 1 out of 4 is the probability to land on blue. So if you spin 8 times, you might expect 2 also, and because every time you would spin 4 times, you'd expect one of these to be blue. And so if you spin 8 times, you'd expect 2 to be blue. It's a proportion. And you can write it like this. This is my probability. 1 out of 4 times will be blue. So how many out of 8 times will be blue? And then you solve by cross multiplication. You'd say, all right, well, 4x should equal 8 times 1, or 8, and you divide by 4 on both sides, and you get 2. You try it with this one, right? How many times would you expect to roll a 2 if you rolled a single die 24 times? Build a proportion like this and try to solve that. Yeah, go. All right, so we know that 1 out of the 6 sides is a 2 is what we want, right? Notice I'm not putting the 2 here. It's just there's one of these on the die, right? There's only 1, 2 on the die. And so I know 1 out of those 6 is what I want. And therefore, if I rolled 24 times, how many of what I want would we expect, right? And so you'd say, all right, well, let's do a little cross multiplication and say, I know that 6x in a proportion, oh, that was a bad choice, 6x should equal 24. And then you divide both sides by 6, and you get yourself, you would expect 4 2's to come out of this. So this really means I would get a 2 4 times, right? And this is the basis of gambling. Great. All right. Oh. So I guess we'll do this with the class that I see, but if you rolled a whole bunch of times, you'd see this happen, that as you rolled more and more dice, you'd get closer to this theoretical probability. You'd get closer to 1/6. And we'll talk about that a little bit in more depth. So in addition to theoretical probability, there's experimental probability, because sometimes we can't just figure out numerically what the probability is, because it's not so straightforward. Let me give you an example, right? So maybe a doctor has an operation that has an 80% success rate. So here's my representation of that. They try to fix somebody's leg. I don't know, like your ACL is broken. They go in and fix that. If they do that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times in the past, they have done it. And out of those, you have these 8, 1, 2, 5, you have 8 that have been successful. In the past, by experiment, we have done 8 out of 10 have been successful, and that's 80%, right? That's where that statistic comes from, is previous history. The experiment is this going to work? And you don't want to be the guy who's experimented on where it doesn't work. So this is experimental probability. You can write this in your notes too. It's the number of times the event occurred divided by the number of times you've tried it. So in this case, we had 10 patients in total, and the number of times the event occurred. The event, what we're calling is the event is a successful recovery from this injury, right? Leg didn't fall off, leg stayed on. So the event that we're talking about is success, right? So how many successes out of 10? So 8 out of 10. You could also have the probability for a failure rate, and that would be 2 failures out of 10 trials, right? So that's experimental probability. So let's try that out. You got a bag of marbles. This is just a really stereotypical experimental probability thing. We don't really know the probability yet, but we're trying to figure it out. So we have marbles that are blue and green and orange, and we have 4 blues and 5 greens and 3 oranges. So the total number of marbles here is 12, right? 9, 10, 11, 12, great. And so the number of blues, if you threw them all in the bag, what's the probability of pulling a blue out? Well, it would be these 4, the four successes, which is 4 blue ones, out of 12, right? And you'd simplify that to 1/3, or 33.3333%. Probability of orange would be these 3 out of those 12, so that'd be a fourth, right? 25%. You try green and purple. Go. Okay, so green, pretty straightforward, 5 out of 12. It doesn't simplify very much, so that's, you'd leave it like that. And purple, oh hey look, no purple. So you have no chances in 12 to pull out a purple, so you have 0% chance, right? Great, it's not going to happen because there are no purples in there. Neat. Okay, so for our last trick, we're going to do the same thing. We're talking about expected outcomes. We're going to solve these using a proportion. So we were looking at blue marbles. Let's try blue. Here's blue. We're going to pull out a marble, look at it, like, oh, record what it is, and then put it back in the bag. We're going to call it, we replace it. So we're going to do that 6 times. So if we did that once, you would expect that out of, let's see, there were 12. There were 4 blues, or 4 blues out of 12, right? And you could simplify that. I'm going to do this with this unsimplified fraction for now. I know that's going to equal this same proportion if we pulled, so if we pulled 12 times, we'd expect 4 of those marbles to be blue with replacement. So if we pulled 6 times, we could expect x, and naturally this is half, so this should be half. This should be 2, right? But you can do it with a proportion, say 12x equals 24, and then divide by 12, and x is 2. Try that with number 2, with orange marbles. Go. All right, so if we want to pull out orange marbles, we have 3 out of 12, right? If we pulled 12 times, we should get 3. And so if we want to pull 8 marbles out, put them back, pull one out, put it back, pull one out, put it back 8 times, you'd expect x out of 8 should be equal to 3 out of 12. And then you can also divide this up and say, okay, this is 12x equals 24, and we should get 2 of those, right, when you divide. Great, same sort of thing. What I'd like you to try, I don't know why I keep clicking on that. What I'd like you to try is this probability sheet. Try some of the problems. Let's go with the odds. I know that there's a bunch of them, but most of them are pretty straightforward. You're counting. So do the odd problems, and we'll go from there. Okay? See you next time, you odd ones.